Welcome to day 2 of our journey through programming languages. Today we will dive into syntax and semantics, the fundamental building blocks that govern the structure and meaning of code. Let's get started. First, let's understand syntax. Syntax refers to the set of rules that define the structure of valid code. These rules ensure that the programming language is structured in a way that the computer can interpret. Think of it like grammar in human language. It ensures clarity and prevents confusion. Now, programming language grammar defines the formal structure of valid statements. This grammar can be represented using Bocas-Norm form (BNF) or extended Bocas-Norm form (EBNF). Syntax is crucial because it ensures that the code is well formed and can be parsed by the compiler. Next, let's explore semantics. While syntax defines the structure of code, semantics defines its meaning. It's about what happens when the code is executed. There are two main types of semantics: static semantics, which are checked at compile time, and dynamic semantics, which are checked at runtime. Why is semantics so important? Well, it ensures that a program behaves as expected. For example, even if the syntax is correct, the program could still produce incorrect results if the logic is flawed. This is where semantics comes into play, ensuring the meaning behind the code matches the programmer's intent. Let's compare syntax and semantics. Syntax deals with the structure of the code, while semantics deals with the meaning. For instance, missing a semicolon would be a syntax error, whereas using an uninitialized variable is a semantic error. When we look at error detection, syntax errors are caught by the compiler during compile time, whereas semantic errors are often only identified at runtime through testing or execution. Understanding the distinction helps developers debug more efficiently. Syntax can be divided into two main categories: lexical syntax and grammatical syntax. Lexical syntax deals with tokens such as keywords and operators, which are the smallest units of code. Tools like regular expressions and finite automata are used to recognize these tokens. On the other hand, grammatical syntax arranges these tokens into valid expressions or statements. This is where parsing comes into play, and context-free grammars are typically used to specify valid statement structures in a language. Here's an example of an arithmetic expression in Bocas Norm form BNF. This grammar shows how expressions, terms, and factors are combined to form valid mathematical expressions. It's the formal way to define how the language processes arithmetic operations. Let's put this into practice. In this activity, identify whether the following code examples contain syntax or semantic errors. This will help you sharpen your skills in recognizing and understanding errors at different levels of programming. Here are a couple of additional activities. First, write the grammar for variable declarations in EBNF. Then consider a debugging scenario where both syntax and semantic errors are present. How would you go about fixing these issues? To wrap up, remember these key takeaways. Syntax ensures the structure, while semantics ensures the meaning of your code. Both are critical for writing reliable, functioning programs. Using formal tools like BNF, EBNF, and parse trees, we can analyze and design more robust programming languages.